So our next speaker is an undergraduate student, Tate Erickson, who's coming to us now from UBC. So his talk is actually going to be virtual, and it's A antigen re-expression and prevention of hyperacute rejection following in vivo enzymatic treatment in a model of ABO-incompatible transplantation. Oh, he's at Queens? I'm sorry. I don't know where he's at, because on his thing it said UBC, so I didn't know. Well, he's at Queens. Oh, good.
Yes, I go to school at
It doesn't
Queens,
say on
but this
here,
work was
but
at the U of A. My name is Tate Erickson. I'm a third-year undergraduate student, and today I'll be presenting the findings from my summer project at the Dr. West Lab, looking at the enzymatic conversion of A antigen in a mouse model and the potential to avoid hyperacute rejection. First, as some background, the ABO histoblood group system currently represents a significant barrier to full organ utilization in transplantation. And this is because crossing that ABO barrier can lead to hyperacute antibody-mediated rejection. And so ABO-incompatible transplants are only performed in a limited number of cases. And so consequently, it's more difficult to match organs for blood group O individuals. And we see this reflected in patient outcomes, where blood group O individuals have a higher mortality rate on transplant waitlists. So current methods for limited ABO-incompatible transplants involve reducing recipient antibodies, but plasmapheresis comes with negative implications for patients. And so this project is looking at a new method. Instead of reducing recipient antibodies, of what if we could reduce the donor antigen to facilitate ABO-incompatible transplantation. And so there are 18 glycan subtype structures in the ABH antigen system. And really what we're interested in is this type 2A antigen, as this is the antigen that's present across all vascular tissue in the human body. So then Dr. Wither's group recently identified a pair of enzymes termed azymes that are able to remove A antigen with high specificity and efficacy. And this is done by converting A antigen into H antigen, which is found on blood group O individuals, where shown through this pathway here, where A antigen is deacetylated by the first enzyme and a galactosamine is cleaved by the second. And previous work on this project has successfully converted human blood group A red blood cells to mimic blood group O, as well as convert human lungs in an ex vivo lung perfusion model. However, the enzymes that are continuously decorating the tissues of blood group A individuals, which are aglycosyltransferases, remain active. And so in vivo, we expect to see A antigen return. And so previous studies have not been able to assess A antigen re-expression, nor assess the clinical relevance of azyme treatment. To address this gap, we applied our A transgenic mouse model, which constitutively expresses ABO-A antigen on vascular endothelium using the ICAM2 promoter. And so our lab has previously used this model to study ABO-incompatible transplantation by supplementing the immune response to cause antibody-mediated rejection during ABO mismatch. We've previously shown the efficacy of azymes in removing A antigen in the A transgenic mouse model, and also finding that 2 minutes of treatment was sufficient to perfuse microvasculature of the heart. Knowing that azymes are active at 4 degrees allows us to enzymatically treat the organs during the time between removal from the donor and transplant into the recipient. So with this model, we sought to evaluate the re-expression timeline of A antigen following azyme treatment and understand the significance of blood group conversion by modeling hyperacute rejection. To do this, we used black 6 mice of both sexes with A transgenic mice as our donors and wild type mice as recipients. In vivo azyme treatment involved injecting mice with 2 doses of azyme separated by 30 minutes, and then heart and lung were harvested 2 minutes after and stored in an organ preservation solution. Hearts were then directly transferred into fixative or heterotropically transplanted into recipient mice with A and H antigen assessed by immunohistochemistry. To model hyperacute rejection, That involved transplanting into the recipient mouse and then injecting the recipient with anti-A antibody and rabbit complement, with subsequent immunohistochemistry assessing A antigen, H antigen, and complement deposition as a marker for antibody-mediated rejection. First, looking at the antigen expression after AZyme treatment and cold storage, we see a large decrease in the amount of A antigen staining. So comparing to no AZyme treatment, both 4 hours and 24 hours show a large decrease in staining, with 24 hours showing a further decrease versus 4 hours. Conversely, we see the appearance of H antigen staining following AZyme treatment, and the lung results are also similar, where we see a large reduction in A antigen staining and the converse increase in H antigen staining across treatment. Before looking at re-expression, it was important for us to show that the transplant alone was not going to affect A antigen expression. And so what these panels show here is that 7 days post-transplant without AZyme treatment does not change the A antigen expression significantly versus a native atransgenic heart that has not been transplanted. And so this is important then in the context where we look at A antigen expression after AZyme treatment and transplantation, where what we see is 24 hours post-transplant, there's minimal and weak A antigen staining present, and all of that staining was localized to the epicardial face of the heart. 4 days post-transplant, diffuse A antigen staining occurs, and A antigen staining looks like an untreated atransgenic heart 7 days post-transplant. And we see a similar pattern in H antigen staining that we saw previously, where as more A antigen staining is present, less H antigen is present. So that's showing us that conversion between the two antigens is still occurring complete and not partial between, as it's a 2-enzyme system. We're not getting stuck in the intermediate. Finally, looking at the results from our hyperacute rejection studies, we tested the hyperacute rejection model both with and without AZyme. In the mouse without AZyme treatment, we observed complement deposition, lymphocyte infiltration, and then also decreased graft function. And this is consistent with hyperacute rejection given the 24-hour time frame that these results were in. And this contrasts from our model with AZyme treatment, where we didn't see the same complement deposition, lymphocyte infiltration, and also had greater graft function after 24 hours. And so it's lacking those indicators of hyperacute rejection. In summary, A antigen was successfully depleted in vivo using AZymes and is gradually re-expressed by heart grafts within 7 days post-transplant. And our preliminary findings with our model of hyperacute rejection suggest that AZyme treatment is able to prevent hyperacute rejection, though longer-term antibody-mediated rejection studies may offer further insight into the relevance of this temporary A antigen depletion in avoiding graft rejection. Clinical application of this technology may permit additional ABO-incompatible transplantation, which could offer life-saving treatment for patients who compatible organs may not be found, and also utilizing organs that may otherwise be discarded. I'd like to thank the West Lab for their guidance and support with this project, along with our national colleagues on the AZyme project. This work could not have been done without funding support for both the project and my summer studentship. With the summer studentship, I received an NSERC Undergraduate Student Research Award, and the project received funding from a joint CHR and NSERC grant. Thank you.
Thank you very much, Tate, for an outstanding presentation. I think we have time for one question. Okay, well, I have a question. So you don't see hyperacute rejection. Do you start to look for antibodies, whether or not you're starting to see antibody depletion against the A antigen, as you start to bring back, because you're now slowly bringing in the antigen? Are you somehow, because you are re-expressing slowly, beginning to tolerize against having the other blood group? Do you know, or is that something that the West Lab is looking at?
Yeah, so the question of tolerance and accommodation are both really interesting here. Accommodation would probably be more likely, where the difference is tolerance is you're not seeing antibodies come back at all, and accommodation is the antibodies are coming back but not causing the graft rejection that is seen. And accommodation might be more relevant due to the effect that has been seen clinically with kidney transplants, where ABO-incompatible kidney transplants, patients who do not actually reject the graft even after their ABO antibodies return. It's just like the antibody levels are there, but not causing, they're not attacking the graft. And whether or not that can occur in this case is a really interesting question, and possibly like one of the main goals would be that since the hours post-transplant are so crucial in avoiding rejection for long-term outcomes, of AZyme treatment could be a strategy to kind of get over that first hurdle. And even though the antigen may come back, ideally, if graft rejection could be avoided as ABO antibodies return, that could be super interesting. It is a limitation of our model where the mouse immune system is not sufficient on its own to cause hyperacute rejection sufficient for us to visualize it. And so then that's why we're using passive antibody injection and the complement injection to supplement the mouse's complement system, which is just not sufficient here. We might be able to do studies with this in the future by sensitizing the mice to a antigen to try and make the inherent natural immune system of the mouse more robust. But currently, it's not something that we've gotten a chance to look at to see if there's an accommodation effect.
Interesting. Are there any? I think we may have time for one more. Is there any other questions? Okay, if not, please join me in thanking Tate for an outstanding talk.